Hello, my name is Joshua Mukherjee and I would like to present LeviStepNet, a novel machine learning approach to acoustic point holography. We would like to generate arbitrary sound fields by defining pressure at key points. At these key points, we want high acoustic pressure. The method we use to generate this pressure is by using phased arrays of transducers, or PATs. We use two grids of 16 by 16 transducers which operate at 40 kHz. In order to generate this sound field, each transducer is given a phase relative to one another. This causes the waves emitted to constructively and destructively interfere. This has the potential for use in a wide variety of different cases, such as haptic feedback for computers. It can also be used for levitation. Small particles can be trapped between lobes of high pressure. This allows for a number of applications such as fabrication, targeting drug delivery by levitating microbubbles of drug, and 3D volumetric computer displays. The phases for the PATs cannot be directly solved for, meaning we need some kind of optimization method to find these phases, a process known as phase retrieval. A common class of functions are the Gerchberd-Saxton, or GS algorithms. They are a class of iterative algorithms that converge on a good solution for the phases of the PATs. Weighted Gerchberd-Saxton, or WGS, is a variant of GS, where on each iteration it reweights the target pressure to find a better fit for the phases. This process is slow, however it generates a very accurate set of phases. By accurate, in this case we mean that all the points of interest have a high pressure, and that across points the pressures are almost exactly the same. GS-PAT is a different algorithm, aims for speed. It can generate around 17,000 solutions per second. However, it suffers from reduced accuracy. More recently, machine learning has been applied to phase retrieval. An example of this is acoustic, which uses a convolutional neural network. Many of these methods have a trade-off between speed and accuracy. Methods such as WGS and DiffPat show very good accuracy, but they are slow. This makes them less suitable for real-time applications. GS-PAT is very fast, and so is ideal for real-time interaction, but suffers from lower accuracy. Machine learning methods have the potential to avoid both of these. acoustic was able to generate highly accurate solutions in significantly less time than iterative GS-style algorithms were able to, because only a single path through the network is required. For all existing methods, when a particle is moved, an entirely new solution needs to be generated. LeviStepNet is a machine learning network which, instead of doing this, learns to update phases to move particles in the desired direction. We start with WGS, and this is only done on the initialization step. Previous phases are passed through a simple neural network in order to reduce the number of features that need to be processed by the rest of the network. These are then passed into a multi-level perceptron, MLP, which operates on each point individually. This results in a set of local features. Local features are then passed into another set of MLPs. The output to these are then passed into a symmetric max function, and as such gives a vector of global features. These local and global features are then passed into a final set of MLPs and to give 512 numbers representing the residuals for the phases of the PATs. These phases are then summed with the previous frame's phases, and the amplitudes are all constrained to be 1. These resulting phases are outputted as this frame's phase, and they are also stored to allow for the computation of the next frame. Additionally to this, the network needs a term added to it to help it avoid large changes in phases between frames. A large jump in phase may cause particles to fall between those frames and the levitation to fail. The figure shows the top and bottom PAT for each subsequent frame when using LeviStepNet, and each pixel represents the phase change of a single transducer. In training, the network was trained using a mean square error loss comparing the pressure of the points of interest with that generated by WGS over 200 iterations. It was trained for 50 epochs with a batch size of 32 examples, and a cyclic learning rate was used to avoid any issues from too large or small learning rates. This shows the pressures of points for the first frame in 8 random sequences for LeviStepNet, as well as 200 iterations of both WGS and GS-PAT. LeviStepNet is able to outperform GS-PAT and is very close in the accuracy achieved by WGS. For a specific geometry, this square setup was used. 4 points start in a square at z equals 0, the blue points, and they end 1 centimeter up in the vertical z direction, which is the orange points. The top figure shows the pressure for the 4 points when moving particle 1 the whole distance, then particle 2, and so on. The bottom figure shows the pressure for the 4 points when each frame a random particle is moved each time. The random motion gives a less erratic oscillation of pressure, but the pressure still quickly drops below the level where levitation is possible. The solution to this is to simply reinitialize the network after 10 frames. This gives consistently high pressure and never drops below where levitation can be achieved. In conclusion, LeviStepNet is a novel method of phase retrieval, as it updates previously computed phases instead of starting from scratch each time. It is able to maintain pressure on points that don't move between frames, while keeping those that do move within the range that can levitate the particles. Because of its core being based on point net, it is invariant to the permutation of its inputs. It also has the potential to be fast. However, this would need to be verified by implementing in OpenCL or similar, and this is out of the scope of this project. Thank you.